We ended the previous video with this nice sort of, I suppose, sculpture-based analogy of how MCMC works, where if I want to sample from a difficult distribution, like the blue one, I throw something around it that I can sample from, such that it covers all the values, potentially and a lot more, the red distribution here, and then I sort of chip away at the excess. So some of the time where the red distribution suggests a point, I will always accept it when that's the right height. Sometimes I'll never accept it when there's no blue there, and sometimes I'll randomly accept it with some probability equal to the ratio of those heights here. Let's do an actual example here, and this also gives us a little bit of revision of eigenvector eigenvalue methods. So let's say we want to sample from the discrete distribution to get realizations of x, such that x has a 10% chance of being 1, 2, or 4 each, and a 70% chance of being 3. But all I've got is I've got something that gives me the values 1, 2, 3, 4, all equally likely. So I want to have the blue distribution, but I've got to start with realizations from the red distribution. So you can sort of imagine that if I got a chisel out, I'd have to cut away a lot of the 1s, the 2s, and the 4s until the red distribution was the same shape as the blue distribution. Never mind the scales being different, but the blue distribution is one where 3 of the bars are of equal height, and the other bar at 3 is 7 times the height of the other. So that's what I want to do. I want to chisel away at the red until I'm left with that. So what I want to do is I want to use this proposal distribution, which is just going to suggest the 1s, the 2s, the 3s, and the 4s all equally likely, all independently after each other. So 3, then 1, then 1, then 4, then 1, and cut away at that until I'm left with something which is 70% 3s and 10% each of the others. Some of the cases are quite easy. The easy case is that if it's in state 1, every proposed move is accepted. Because if I'm in state 1 and it proposes going to state 1, or state 2, or state 4, then I'm in a 10% chance move. It proposes going to a 10% chance move, so that ratio is 1. If it proposes going to a 3, well, that's 70% divided by 10% is 7, so that would also correspond to a probability of 1. Note that I've ignored the G here because drawing independent draws from 1, 2, 3, 4 uniformly at random, there is no asymmetry in there, so the G terms will cancel each other out. So what this does mean is if I'm in state 1, every proposed move is accepted. By the same argument, well, there's no difference really between state 1, state 2, and state 4. So if I'm in state 2 or 4, for the exact same reasons, every proposed move is accepted. So in state 3, that's a little bit different. Because if I'm in state 3 and it proposes going to state 3, then by definition, the probability of state 3 is equal to the probability of state 3. So that's 70% divided by 70% is a probability of 1. But in the other case, if I'm in state 3 and it proposes going to 1, 2, or 4, then I want to say, well, I could do that. But state 1 is 1/7 as likely as state 3. And I could go to 2, but that's 1/7 as likely. So what I want to do is I want to, every time I propose leaving state 3 for a less probable state, I want to make a random decision such that I will do that sometimes, i.e. 1/7 of the time, but the 6/7 of the time will reject that move and stay in 3. If I do that, I get a transition matrix for the Markov chain that looks like this. So I'll start with the first row, second row, and fourth row. Those just simply say you propose any of the four moves, all equally likely, and all of them are accepted. So each of the moves happen with probability 25%. That's straightforward. The third row is a bit trickier, because in order to go from 3 to 1, I have to propose going from 3 to 1 and then accept that move. So the chance I propose it is 0.25, and the chance that I then accept it is 1/7. So the chance that I propose it and accept it is 1/7 of 0.25. Same for going from 3 to 2, same from going from 3 to 4. Now, the chance that I go from 3 to 3 could actually happen four ways. I've either got proposing going from 3 to 3, or proposing going 3 to 1 but rejecting it, or proposing going 3 to 2 and rejecting it, or going 3 to 4 and rejecting it. So what I'm left with is I'm left with the 0.25 probability associated with proposing going 3 to 3, plus 6/7 of the 0.75 probability of leaving state 3, but then rejecting that. And if I work that out, that gives me 6.25 over 7. So now I can reach for the eigenvector eigenvalue methods to verify that this does indeed give me draws from the target distribution. So I'm claiming that the target distribution, which I'm going to get to using this proposal distribution and the Metropolis-Hastings acceptance probability, is 10%, 10%, 70%, 10%. So if it's the equilibrium distribution, that probability vector times the transition matrix will give me that probability vector unchanged. And when I work that out, sure enough, I'll just do, for example, the first one. The first element will be 10% of a quarter plus 10% of a quarter plus 70% of a quarter over 7 plus 10% of a quarter is 10%, and so on. If I work all of those out, sure enough, that does give me the equilibrium distribution. Now, this is more of a lead-in for the 11th and final week of videos. The real reason MCMC methods have come so much to the fore in the last generation or so is tied to Bayesian statistics. And Bayes' theorem is tied to often inverting conditional probabilities. I know an event A given probability of A given B, but I want the probability of B given A. So this is often used in things like medical screening. I may know what's the chance of a medical procedure scanning a patient properly if I knew the patient's health status. But if a patient only has the scan results, what they want to know is, given their scan results, what's the chance of them having a particular true health status? So this is fairly routine. We've already relied on it once this week to work out conditional probabilities, that the probability of A and B is the probability of A given B times the probability of B, which is the same as the probability of B given A times the probability of A. And this is Bayes' theorem, just in terms of inverting these conditional probabilities, named after Reverend Thomas Bayes. The obvious question at this point being, how does this tie to MCMC methods? Well, if I do the continuous equivalent of this, then if I want to work this out, the hard part is the calculation of the denominator, where I have some uncertainty about the variables, potentially with some uncertainty about the parameters, theta. So I'd have to integrate out over that uncertainty. Or in the discrete case, sum over those. But the great thing about MCMC is I don't need to ever work out those denominators, because the acceptance probability is based on a ratio of how likely is it in the proposal distribution to how likely in the target distribution. So the great thing about that is that the hard part of this calculation will cancel out. So I can write down a definition of distributions, which might be too hard for me to even get a nice, tidy analytical form to say, here is the distribution I'm sampling from. But I can still sample from it, even if I can't easily write down a tidy form of it. And that's where MCMC really intersects with Bayesian statistics. We'll see more of that next week, but I can sample from difficult models, even when the model might be too difficult to write down in a nice, tidy form.